If a charged particle moves through a field, how much energy does it gain? And does it matter whether or not it's positive or negative energy? So first of all, what is electric potential energy? Just like how gravity pulls down objects and increases their speed, an electric field pulls charges and it does work on them. The work that gets done gets stored or converted as electric potential energy. If the force is conservative, which electrostatic force is, we can define the potential energy equals negative work. Just like with gravity, going with the field lowers potential energy and going against it increases potential energy. For example, if you have two charged plates like this with a uniform field in between, with this side being positive and this side being negatively charged, and you place a tiny positive test charge near the positive plate, is this, and let it go, because it flows from positive to negative, your test charge is going to accelerate toward the negative side. The field does positive work. So the charge's potential energy gets converted into movement, which means that the charge's potential energy decreases. That's why this formula exists. The mechanical equation for work is force times distance. You're familiar with this, but in electricity, it's charge times the electric field times the distance traveled. And since potential energy is equal to negative work, like we discussed 5 seconds ago, then we can sub in this as work, so QED. This is the equation for uniform electric fields, meaning flat plates or zones with constant strength. This is on free cheat sheet in the description along with every other formula for the topic, but the directional logic behind this is that if the charge is bigger than 0, then it moves with the field, so potential energy goes down. If the charge is negative, so smaller than 0, then it moves against the field's direction, which means that the potential energy also goes down because force and displacement become opposite. The displacement is this way, but the force is this way. Opposite energy still converts. So potential energy is always going down no matter the charge. If the field moves it, then that means work is being done regardless of the charge value, and that means potential energy is changing as well. Here's a new concept, it's called electric potential, and it's represented by V. So instead of thinking of terms in energy, we think in terms of energy per charge. That is electric potential. So the potential difference between 2 points, so difference in potential, is VB minus VA, the potential at point B versus the potential at point A. It's equal to potential energy at B minus potential energy at A, divided by the charge. It's equal to negative work over charge, since this is equal to work. This is how much work per coulomb that the field is doing. So per amount of charge, it's doing this much work. That is electric potential. Here are some units really quick. In case you forgot, energy is measured in joules and charge is measured in coulombs. So potential is measured in work or joules per coulomb, C, equals volts, V. So 1 volt equals 1 joule per coulomb. It's named after this guy, Alessandro Volta. That's where volts come from. Here's a real interpretation. A higher potential means a positive charge would rather be there. It would prefer to be in a place where there's high potential. If there's low potential in a position, it gets pulled there. For example, and if you imagine a hill, a positive charge would want to roll downhill. A negative charge would want to roll uphill. Why? Because a negative charge feels a force that's opposite to the path of the electric field. The force is against it. For the positive charge, both the field and the force are pointing in the same way. So let's go back to that plate setup, which was these 2 plates with the uniform charge. And we had a positive side and a negative side, and we dropped in a positive test charge Q. If this test charge, if we use a negative one instead of a positive one and we place it near the negative plate, it's at low potential. If it's allowed to move, it's going to accelerate against the field. So it's going to go this way toward the positive plate, which means it loses potential energy and it gains kinetic energy because it starts to speed up. But what's still consistent is that the field E is still doing work. So energy was still converted. And the final energy equation, which is a much more general one, is that the change in potential energy for our system is equal to the charge multiplied by the change in volts. This is our main tool. It's on the cheat sheet as well. And if you know the difference between potential and you know the charge, then you're able to find how much energy was gained or lost. I know we went a little bit fast in this video, but to lock this concept in, let's think about a gravity analogy. Think about a cliff and you drop a rock off the cliff. When the rock is at a higher up position, that means there's more gravitational potential energy. When you go lower and lower, more of this potential energy has converted into kinetic energy as you speed up, which means that there's less potential energy left over. And eventually when you hit the very bottom, you're at maximum speed, which means maximum kinetic energy and zero potential energy. Let's tie this in with electricity. It's the same. With electric, instead of gravitational potential energy, which has a formula mass, gravity, height, you have potential energy equals charge times V. When the rock falls from a high height to a low height, it's like a charge moving from a high V to a low V. And if your rock is heavier, that means there's more energy. And if there's a bigger charge, that means there's more energy. This is the best analogy I could come up with. And it fits perfectly. Here's an equation summary before we solve our first problem. If you don't care, go get the cheat sheet. We can skip this part. Potential energy change is equal to charge times VB minus VA, which is equal to the charge times the change in V. For a positive charge moving from a high V to a low V means a loss in potential energy and a gain in kinetic energy. For a negative charge, it's inverted, but it still works because the charge sign is built into the charge. So let's go through an example problem now. Let's say you've got a giant potential difference of 5,000 V. You drop in an electron, what happens? Yes, it's pretty vague, but let's go through our goals first. First, we're going to find the change in potential energy. We're going to find the change in kinetic energy, and we're going to find the final speed of our electron, so final velocity. Let's solve. We're given a few values. The change in V, which is VB minus VA, is 5,000. The charge of an electron, you can Google this, is negative 1.6 times 10 to the power of negative 19 coulombs. And the mass of an electron is 9.1 times 10 to the power of negative 31 kilograms. It's pretty light. Why this matters is because our formula, remember, is change in PE equals charge, change in V to get the energy change. Right? That's what we're solving for here. So we need the charge and we need the change in V to find potential energy. Later on, mass is going to come into play for speed because obviously if your thing's heavier, it's going to be harder to go fast. Let's sub in our values. So change in potential energy is equal to the charge, which is negative 1.6 times 10 to the power of negative 19 coulombs. I keep forgetting to write the 1 there. Multiplied by the change in V, which is 5,000. The answer to this is negative 8 times 10 to the power of negative 16 joules of energy. So this is how much the potential energy changed. It's negative because the potential energy went down. The energy was released and turned into kinetic energy. And since energy is conserved, that means all of the potential energy that was lost had to go somewhere. And where did it go? Kinetic energy, which means that kinetic energy is equal to the loss in potential energy, but as gain. So it gained the amount of potential energy that we lost. Conservation. So we just solved both A and B right here. All of the potential energy turned into kinetic energy. But how about for the final question, which was the final velocity of our electron, which was dropped in with this voltage change? Since we know the kinetic energy and we also know the mass, it's very easy to find velocity. If you know the kinetic energy equation, which is kinetic energy equals 1 over 2 times mass velocity squared, then you can rearrange for velocity with your excellent math skills, which I hope you've been developing, to find V equals root 2 charge of V divided by mass. Plug in our values for charge, which is negative 1.6, blah, blah, blah. Voltage is 5,000, mass is 9.1. And your answer is 4.2 times 10 to the power of 7 meters per second. That's what the final speed of your electron is. That's over 10% of the speed of light. So electric potential, V, does not care about mass. The formula does not involve mass. That's why electrons can accelerate so fast. It's the same voltage, but they're way lighter than protons. And the mass only matters when we're looking for velocity. So when you apply a potential difference, you're not creating a force out of nowhere. You're giving charges the opportunity to gain energy. And how much they gain depends on their charge and the voltage they cross.